I posted a video today that was a demo of this sort of walking simulator. So what you're looking at here is I'm kind of marching in place in my play space. You're looking at a recording from the Quest. This is my play space here. I'm sort of marching, turning, etc. So this was the demo video I released a couple of hours ago, and I just felt the need to kind of step through just sort of the current state of the art with the code in this project, mostly for my own sort of recall. And, when I revisit this a couple months from now, I want to make sure I kind of have a sense of what I was doing. The project is called udnat, which is just a working name. It's You Don't Need a Treadmill. I was thinking about buying a treadmill for my apartment, and they weigh 300 pounds, which is a deal breaker for me. I live in a very small apartment, and I didn't want to cruft up this space with a giant treadmill, not to mention the noise for the neighbors. So anyway, what we've got in this project is this was essentially started with the Unity stock VR template, this guy. So this XR Origin is an unmodified version, mostly unmodified version of the XR rig. I think the only modification is I turned on gravity, but that's basically it. And then the custom code is this object. It's an empty game object. There's three components to it. The walking gauge provider is maybe the easiest to understand because all it's doing is listening to the left trigger and toggling is walking or is not. So the way the script works, and I wanted to keep this a secret, but there's going to be more value in talking about the science of this rather than thinking of this as some sort of dark project. But the way this script works is as you're walking and you're pumping your arms, it's looking at the translation vertically of your hand movements and extrapolating sort of a walking velocity from that. And that's what this speed provider does. But just the simplest component is, do we want to activate walking or not? And that's what this engage provider does. And this just surfaces a public is walking Boolean. So one of the things I had to deal with, and there was an older first version, is you notice that all of these scripts have references to the new input system, and specifically this default XRI. This is in the folder starter assets samples. This is 3.21 of the XRI toolkit, XR interaction toolkit, and these are the input actions. These are the stock input actions, and you'll notice in the walking gauge, the one it's looking at is XRI left interaction activated. If we dive into this, we see that it's bound to the trigger button on the left-hand controller. So this is a Quest controller. It's got a, let me see if I can bring up really quickly. So the trigger button is like kind of that thing, right? There are two of them. There's one on each hand. So essentially we're using the input system to listen to this button click. And so you enable the action, you disable it on exit, and then you just bind a listener, and that listener toggles that public Boolean. So when you bind the listener, you're basically just, this is where you add this function on click to the queue, to the sort of callbacks. This is a publish subscribe pattern. So we're just adding our own click listener, and it's doing. Again, I try to make this kind of modular. All it's doing is surfacing this is walking Boolean. So as you click the trigger, it's going to check or uncheck. And then the controller has a reference to that. As we see here, it's got a reference to the walk engage provider. And then the second provider is the more complicated one, the speed provider. And what we notice is that it's looking at 3 pieces of data from the XR rig, or more specifically from the input system. And that's a point I want to make here is in the first version, I literally just went into XR Origin and found the left controller and the right controller, right? And dragged them in. Here, the type was game object, drag them in and then just asked the game object for its transform and position. Remember, again, we're tracking the vertical position of the controller. So as you're walking and pumping your hands, that's how we're deriving speed. So let's take a look at this controller script. So we notice now that instead of game objects, though, for the walk speed provider, we've got input action references. And again, that's referencing this system, this XRI default input action system. And this is also just very simply surfacing a kind of signal, and the signal is abstract, but it scales. The faster you pump your hands in conjunction with marching in place, the higher the signal gets, and we're using that to drive the movement forward. There are some parameters, so the math is a little sort of right at the boundary of what I'm able to comprehend, but this is essentially, I think it's basically a low pass filter. So there's 2 sort of tuning parameters to the function that we'll look at in a second, and then all we're really doing, we'll cover what I just scrolled through in a second, but all we're really doing is taking the Y position of the left. So let's look at one controller at a time because it's just an average of both of them. So we're taking the current Y value, we're getting the delta from the last Y value, and then we're computing the vertical velocity, which is just distance over time, right? Then we're updating, and we've got this first tuning point where we're taking, it's the absolute value of vertical velocity, because vertical velocity can be negative if your arm is descending as you're walking versus ascending. So this is the first tuning value. It's just basically, think of it as a constant. I surface it in the inspector if you want to mess with these values to get things working. And I found that, depending on what the collider is on the terrain, so this, let me see if I can even find the terrain. This terrain has a terrain collider, which is essentially a mesh, and you're pushing and pulling the mesh to form the terrain. And that behaves subtly differently than just a flat box collider for a plane. And that's when you'd really want to, oops, what happened? That's when you'd really want to, we're still recording? Yeah. You'd want to tune those tuning parameters. So like you might reduce the damping if walking is going too slow or something. And again, just to so we don't lose context here, what we're trying to do is drive the platform forward as we're walking, right? So we need to there is no, we're not moving in the play space other than marching in place and turning. So there is no actual forward velocity of the headset. We're having to extrapolate it from arm movement. So that's the context again. So anyway, in this walk speed provider, we're basically just computing the vertical velocity, and then the math is first we've got these options for how to combine them, and I basically just program these in because some of this is AI assisted coding, and I wasn't exactly sure which one. I ended up with just an average, just average the left and the right, left plus right divided by 2. So that's how you combine them, and this math for how you smooth them. So this is the smoothing function. We're lerping from the old step signal to the new step signal. So remember, this step signal is increasing as we go faster and decreasing as we go slower. So we're interpolating towards the new value, but we're only interpolating a portion of the way there based on this t. And there are 2 options for how to sort of damp the interpolation. One is just a straight scaling of a damping factor by time delta time. You don't really have to understand this math. And one is sort of more, it's called exact exponential decay coefficient. It's doing this. I think this is the one I've tested. It works pretty well. There's a general formula for a low pass filter, and you have to understand the lerp command. But essentially, what we're saying is don't jump all the way to the new signal. We want to interpolate towards the new signal over time and in a sort of damped fashion. You can think of damping as a spring and the spring rate. So if I put force into a spring, if it's a really light spring rate, if you think about driving a motorcycle down the road, if you're too heavy for the bike and the springs are too weak, when you hit a pothole, you're going to bottom out the spring because everything moves really fast. It compresses, when you hit bumps and potholes. And that's why this is called a low-pass filter. So anyway, so what we're basically doing is now surfacing this step signal, which is abstract. It ranges from about 0 to 2, more or less. And we're using that to finally drive this controller. Notice the controller has a reference to the engagement provider and the speed provider. The engagement provider, again, is the trigger depressed so that we know we want to walk. And this one is providing that speed signal. So let's just quickly have a look at the controller. So the magic here, so we're doing some checking to make sure that things we need are not null. And the first thing we're doing is we're checking the engagement provider to make sure we're walking. And if we are walking, we're going to execute some code in update. And move is essentially 2-part function. Calculate the movement vector based on that speed signal. So the faster we're moving, the larger the magnitude of the movement vector. And then essentially, we're going to apply the movement to the character controller in the XR rig. So the character controller is a component of the XR origin. It's actually the same character controller that you'd use in a non-VR project. I'm experimenting with applying the movement directly to the XR origin, but there's a problem with gravity. I haven't really worked on it, so I'm applying it to the character controller. And just to calculate that vector, all we're doing is so this is a little nuanced, but what we want to do is we want to move in the direction we're looking, right? So we take the the camera from the XR rig, and we find its forward vector, and then we kill its vertical signal. We normalize it, and then we multiply it by that signal that I spent so much time talking about. That signal is, again, proportional to how fast we're moving, and then we have just a very typical speed public variable. This is a tuning variable. It's surfaced in the controller. This video is getting way too long, but it's surfaced in the controller just as a tuning variable to just abstractly how much forward you want to move each frame. So that's really it. All the controller is doing is saying which way is the camera pointing, and then let's move forward along that. And it's broken up into sub functions so that I can play around with what we're applying the movement to, and all like that. So that's basically the whole project. Now, this video is already too long, but I think in a subsequent video, we're going to have a conversation about locomotion providers. So in the XR rig, when you interact with the controller, like you hit the button and you jump, or you move the joystick and you move or turn, there is a pattern and a fairly involved abstraction around how these are doing basically the same thing. They're reading from an input and they're routing signal back to the XR origin to move it, turn it, etc. There's a bunch of layers of abstraction with how Unity has built the XR rig. And we're going to have a conversation about maybe converting all of this code into just a locomotion provider that's more standard. This is in the pattern of those locomotion providers. Like it's modular in the same way. It's just not using the same, like if we look at just jump really quick, this will be a future video, but there's a lot of, it's not, this script doesn't directly talk to the XR origin. It talks through an intermediary, so we'll have to take a look probably to get some better insight into how the XR rig is actually composed by Unity, the sort of standard patterns. We'll talk about converting the udnat code to locomotion providers. We're not 90%, we're 70% of the way there. It's just a matter of wrapping your head around the levels of abstraction in this code. Anyway, that's the whole project. The thing I'll close with is the graphics you're looking at right now are an asset store asset. And it's a low poly asset. And I'm dog fooding this app. I need to get as much movement in my life as I can. And, with the low poly asset, it's playable and interesting. And this world is big enough to wander around in. And probably eventually I'll know where I'm going in the world as opposed to getting lost. But also in terms of PC VR, I've been having a lot of luck with, oops, that's not what I wanted to open. I've been having a lot of luck with AirLink. I know a lot of people use virtual desktop, but I've been having a lot of luck with AirLink and using the same infrastructure, but instead of deploying to APK and pushing it to the Quest headset for standalone mode, I just ran into a tree there. Instead of pushing it to the headset, using it over wireless AirLink and having a gaming PC drive the graphics, so then I can go into the Unity asset store and just get a more compelling environment. Sorry that was so long, but that's essentially the whole run through, and I hope somebody gets something out of that, or just talking to my future self. I hope where I'm at now is a little bit quaint for where I want to be in 6 months, but make you feel like I'm making some progress, and this is a good milestone. So thank you so much for watching, and feel free to leave me a comment.